Hello and welcome everyone. My name is Steffen Hädrich. I'm with Active Fiber Systems, a fiber laser company based in Jena, Germany. And I would like to present our results on CEO stable pulses from a 1.1 kilowatt fiber CPA system. This work has actually been done in the framework of developing a laser system for the Eli Alps research facility in Szeged, Hungary, which is also a partner on this work. And furthermore, we were collaborating with institutes in Göttingen and Berlin in Germany. So let me start with a few applications of high repetition rate ultra-fast lasers. They are used in materials processing, or they can also be used in generating secondary radiation, for example, via the process of harmonic generation. And at higher energies, they can also be used for particle acceleration. So first of all, to enable these applications, you need to have a high peak power and or high energy of your laser pulses. And to increase process speed or improve signal to noise ratios, these systems ideally run at high repetition rates and high average power. And this is actually a motivation of AFS's work. So Active Fiber Systems was founded in 2009, and our mission is to rapidly transfer research into reliable, commercially available systems. Our main market is in research, so ranging from fundamental to life science to materials processing. And today we are a technological leader for high power ultra-fast fiber laser systems. We recently moved into our new building, which you can see in the back, which has more than 1,500 square meter of lab space and more than 1,000 square meter of office space. And as you can see here, over the recent years, we were rapidly growing a number of people. So our products can cover a large range of parameters or wavelengths. So we have 1 micron systems, 100 watt class or multi 100 watt kilowatt class systems, 2 micron lasers, OPAs, oscillator systems, burst modules, dual wavelength lasers, and also high power XUV beamlines. And in this talk, I would like to focus on the combination of a high energy, high average power ytterbium amplifier system with the possibility to generate few cycle pulses via post compression and CEP stabilization. So the motivation behind that is the construction of the high repetition rate or HR laser systems for the Eli Alps research facility, which is done by Active Fiber Systems. And the HR lasers are 2 of the 6 main laser systems that are used in the facility to drive attosecond beamlines. So here you can see an overview of the parameters of the HR1 and HR2 laser system. HR1 is a 1 millijoule, 100 kilohertz, 100 watt fused cycle laser system with CEP stability, and HR2 has very similar parameters except for a 5 times higher energy. So HR1 has already been delivered and is soon to be upgraded for CEP, and HR2 will be installed in 2021. So here you can see a brief layout of the laser system. So we start with a CEO stable oscillator, which is preamplified, and this preamplifier already includes pulse stretching, pulse picking, and spectral phase shaping. And then the actual amplification is done in 16 main amplifier channels, which are coherently combined. After that, pulses are compressed in the CPA compressor and then sent into the spectral broadening and compression stage to achieve the HR2 output parameters. So this is a look on the HR2 laser system in our lab. Actually, if you go to our new website, afs-jena.de, you can join a virtual lab tour, and you will be able to walk around this HR2 laser system and have a look on your own. So you're very welcome to have a look how it's looking in real life. So this is a closer look into the main amplifier part of the system. We have 16 main amplifier channels in total, 8 on the bottom, 8 on the top. So there's 2 floors of main amplifier channels. So, and the incoming pulses are split, then amplified, recombined, and then compressed. So here's a measurement of the output of the system running at more than 10 millijoule, 100 kilohertz, which is an average power of more than 1 kilowatt. The compressed pulses are less than 300 femtosecond in duration. And as you can see here, over 9 hours, we measured the power of the system. And in this time range, it only fluctuates by about 0.3% RMS The same is also true for the pointing of the system, which is shown here. The beam pointing is as stable as 6 microradians or 12 microradians in X and Y respectively, also measured over this 9 hours. And we also measured an excellent beam quality of M square 1.2. So here's again this sketch of the laser system with a bit more details on the spectral broadening and compression part. So in this case, we employ a up to 8 meter long hollow core fiber, which is used for the spectral broadening. And then the temporal compression of the pulses is achieved in this compressor here to finally realize the 6 femtosecond 5 millijoule 100 kilohertz output. In our case, we use a stretched hollow core fiber to realize long lengths. This is work that has been done in collaboration with Laser Laboratory in Göttingen, Max Born Institute, and also the Institute of Applied Physics in Jena. And by stretching this fiber, you avoid bending, and this allows for the lowest possible propagation loss, which makes this concept very well adapted to high average powers. So we tested hollow core fibers with 400 micron inner diameter and a length of 6 to 8 meter, which we fill with argon gas. And in our case, we apply a pressure gradient, which means that at the input, we have a lower pressure of 800 millibar and a higher pressure of 1.9 bar at the output of the fiber. So in the first set of experiments, we used up to 580 watt or 5.8 millijoule of this sub 300 femtosecond pulses. We launched these pulses into a 6 meter long fiber in this experiment. And as you can see here on the right side, when we increase the input power into the fiber, the output power keeps rising continuously. And that means that also the transmission stays more or less constant across the whole range of parameters up to the full available input power. And at more than 300 watt of output power, which is the maximum we got in this case, beam quality looks very nice and excellent beam profile here. So of course, we also measured the compressed pulse duration. So this is shown here on this D-scan measurement. And in this case, we were able to achieve significant spectral broadening and finally pulse compression to a bit less than 10 femtoseconds measured via this D-scan measurement. So and in total, we were able to produce 320 watt of average power at 100 kilohertz repetition rate with only about 10 femtosecond pulses. And this output parameters, even if it's an intermediate step in this HR2 project, are already the highest average power ever demonstrated for a few cycle laser system. So of course, the other important parameter is the CP stability, which of course is to a great deal determined by the front, which is a CEO stable oscillator, which we have measured here. So you can see the power spectral density and the integrated phase noise. And in our case, the oscillator has about 100 milliradians of integrated phase noise in a frequency range from 10 Hertz to 20 megahertz. We also employ CP preserving pulse picking in our system, and we make sure that we have the most stable system design possible to also ensure best CP stability. Of course, when building such a system, there are some open questions. For example, how does the large stretching and compression affect the CP stability? For example, if the grating compressor introduces additional noise. And another important question is, does the coherent combination process somehow affect the CP stability of the system? So to have a look on that, we performed an experiment on investigation of the CEO stability when running the CEO stable oscillator at full repetition rate. So we implemented an electro-optical modulator in our system, which will be used for feedback. And then we can run a system with up to 16 channels and 1.1 kilowatt of average output power after the grating compressor. We use a small portion of this output to send it into a nonlinear pulse compression stage, followed by a supercontinuum generation stage to generate an octave-wide spectrum. And then we have a first F to 2F, which is used in loop for generating a error signal and which is fed back via CEO locking electronics to the EUM in the system. And then we have a second F to 2F interferometer, which is used to measure the CEO stability out of loop. And this approach actually allows us to study some general noise properties of the system and also of the coherent combination process over a large frequency range as well. So this is a measurement of the CEO stability of a system with running with one channel and with a free running system. That means the oscillator is CEO locked, but the rest of the system is free running. As you can see on the left side, we have a power spectral density, and on the right side, the integrated phase noise, which amounts to about 700 milliradians in this case. But the actual important message here is that most of the noise is in this 1 kilohertz acoustic region here, which is very well suitable for a feedback loop to be compensated. So this is actually what we did. We employed this feedback mechanism, and by doing so, we can fully suppress this acoustic noise below 1 kilohertz. And this leads us to a CEO stability of only about 220 milliradians. And more importantly, we did a cross-check with the out-of-loop measurement. And as you can see, except for some minor differences, we end up with the same value of the CEO noise here. So we then went on to also characterize the system running at more channels and more power. So this is again power spectral density on the left and the integrated CEO noise on the right. In this case, for one channel, the result I have already shown. And then we increase the numbers of channels from 1 to 2 to 4 to 8 and finally to 16. And as you can see, essentially there's no difference between those measurements. So in every case, we end up at around 220 milliradians of phase noise. And this proves that the coherent combination does not affect the CEO noise of our system. So of course, the more important part is happening here at this fuse cycle output. So as a next step, we started to measure the CEP stability of this fuse cycle output. And this is done by using a stereo ATI phase meter. In this case, a commercially available system from also a company based here in Jena, Germany, Single Cycle Instruments, which provided us with the ATI phase meter, which is actually capable of measuring each and every shot of the 100 kilohertz pulse train to give us the full information on the CEP stability of a system. So the first measurement that we did is shown here. Again, on the left side, the CEP noise power spectral density, and on the right side, the integrated phase noise. And as you can see here, most of the noise is actually located at high frequencies. And we investigated this a bit further in detail, and we were able to trace back some of the reasons for that. And in the first improvement, we could significantly reduce this white noise level here, as you can see on the power spectral density. But more importantly, it also reflects in the integrated phase noise, which is significantly reduced here at this high frequency range as well. And then when we employ the feedback mechanism here, we are able to suppress the acoustic noise again. And with this approach, we were able to show something like 580 milliradians with the feedback loop activated, actually integrated over the full available frequency range of 10 hertz to 50 kilohertz in this case. So that means this is the full available information that we have. So we are further improving this important parameters. So we found a few more reasons for this white noise. So we are currently changing some parts of the system. And as an intermediate result, we were just able to further reduce this white noise part a bit below 400 milliradians already. And the next improvement is already on the way. And we are confident that we can go to this sub 300 milliradian regime that we have also demonstrated in previous publications. So to summarize and give you a short outlook, so I've presented a long-term stable 10 millijoule, 1 kilowatt, 300 femtosecond fiber CPA system, which is the driver for the HR2 laser system that will further consist of a spectral broadening unit that has already run at multi-millijoule free cycle pulses at 100 kilohertz. with an average power of 320 watt. We have shown that the system is capable of providing more than 1 kilowatt CEO stable pulses, even with 60 main amplifier channels running. And in this case, we were able to achieve 220 milliradians of integrated phase noise. And we are currently working on the CP stability of the final system output, which has already shown 580 milliradians with feedback. We already have a first improvement towards 400 milliradian ready, and the next improvement step is underway, and we are confident that we will soon end up with sub 300 milliradian of CP stability at this few cycle output. So with that, I would like to thank you very much for your attention.